Hey guys, welcome to part two of our OpenCV workshop. We're really excited that you guys were able to make it. That being said, just a couple of reminders, housekeeping rules. If you have a question, please message it in the chat. Someone will get to you. But if it can be answered through the chat, there's another sessions for just for troubleshooting, so just hop on over there. If not, I'll hand it over to Lewis and Matthew to get things started.
All right, hello. Can you hear me? Sick. Let me just get ready. Let's turn my video so you guys see the screen better. And you can click twice to maximize Lewis's screen. All right. Hey guys, welcome back to our OpenCV workshop. So we're now in part two of this workshop. And this part of the workshop is where we really turn it up. And we're going to start by creating a lane detection program in this workshop. So, but before we do that, we just want to do a quick recap of what happened in our last workshop. So I can get my slide ready. So let's just do a quick recap. So basically in last workshop, in workshop one, we did, got it. Yeah, so basically in workshop one, we started off by learning the basic functions of OpenCV, such as ImShow, ImRead, thresholding, noise cancellation, blurs, HSV, and many more. From there, we created an advanced color filtering program using the HSV color filter. And by using the track bars, we can determine the exact value of hue, saturation, and value. We then went to more complex methods of OpenCV functions, such as HOUGH space, warp perspective, CANNY edge detection. And we then created a region of interest in which we took the dimension from the skeleton code to create a snippet of a certain part of the screen. All right, so that was just a quick recap of what happened last workshop. Let's move on to what we're going to do today. So what are we going to do today? So we're going to build on the concepts that we learned in workshop one to create our advanced lane detection program. So we're going to first import an MP4 file video to read, then resize the frame to create an ROI, and create a bird's eye view using an ROI and warp perspective method, detect lanes with CANNY edge detection, color filter frames, and then use HOUGH lines method to create vertices or for edges. Then we're going to draw lines on the image using polyline method, create a center line method, and create a center line ROI. So those two methods, the center line method and the center ROI method, we give it to your skeleton code because it's a bit complex, so it'll be hard for you to type along with it, but we'll explain it in depth when it comes to it. All right, cool. So now moving on what we're going to do today. So, all right, so we're talking about the IMUtils library. All right, so how can you, wait, second. Sorry, a second, just good. All right, yeah, so the IMUtils library. How can you alter an image? Well, there's a lot of things you can do. You can crop it, an image, you can rotate it, you can resize it, you can shift it to the right. There's an endless list of possibilities. IMUtils does all of this and even more. IMUtils is a library of basic image processing techniques that allows you to do all sorts of things to images. For today's purposes, we will focus on the resize functionality inside IMUtils. We'll use IMUtils resize method, IMUtils.resize, to lower the resolution of our video. This in turn will increase the processing speed of the video due to less pixels. So you may ask, why are we doing this? So this is just a good practice to do when you're working with any video, as it's important to have better processing speed when running your program. Please do note that IMUtils can also be used to resize a video to a high quality. So let's say in the final product, you want to show a client a really high quality video of your program. You can use IMUtils to give a really high quality resolution. All right, sick. Now let's just move on to, let's do a quick recap of ROI, because in this program we use ROI a lot in the first part of the code, so it's an important concept to fully grasp. So the region of interest are used to create snippets around a certain area. By doing this, we are able to completely eliminate any noise that is outside the ROI without using any image of our blurring techniques, which is really good for processing, but more importantly, for fighting against noise and eliminating noise completely. So how are we able to do this? We're able to do this by creating vertices around the ROI and create a mask around that area. These vertices represent a grid location of a pixel on the screen. This concept of a vertice being a location on a grid is important to understand, as by using these vertices, we can go into applications of ROI, which we will do today. All right, so let's just move on to the main program then.
So at this point, everybody should open up their PyCharm, and we're going to start using the skeleton code that should have been within the doc that you downloaded. From here, everything should be laid out for easy, I guess, scripting for the rest of the methods as we complete them. So this is what the skeleton looks like. I'll just give you a second to open it up. And yeah, so you should notice that most of the methods are empty. And today what we're going to be doing is we're just going to be filling in the gaps, and I'll be explaining the logic and basically how each one of these methods functions based on how we've scripted it. Okay, so getting on to the main program, we're then going to start with our generalized change perspective method. So within or based on the fundamentals that we have learned within the first OpenCV tutorial, the concepts of region of interests can be very helpful in filtering out unwanted noise, as we saw. And using these fundamentals of pixel locations and vertices, we're then able to utilize the built-in OpenCV methods called CV2 warp perspective and CV2 get perspective transform. So those are the two main methods that we're going to use for this user-defined function. The purpose of this function is to warp the perspective of the region of interest into more of a two-dimensional image than a three-dimensional image. So as you can see on the images on the given slide, there's a lot of depth to any given image, and this can actually change how our program will perceive lines on the road. And given within our HOUGH lines methods, we actually have to specify, especially for our probabilistic HOUGH lines, we will have to specify a min and max line length and gap. So as you can imagine, as there is depth perceived, we'll actually lose accuracy. So because the line here will get longer, or the actual line here will be shorter than lines that are closer to our car. So by warping the perspective, our program will get a more accurate representation of what it is trying to find. And so it's important to note that all of the computations that we're going to be doing on our given frame are going to be our perspective warped frames, because it's easier for our script to read this. So now what we're going to be doing, just to generate a get perspective method, we're going to be determining the frame size. And as Matthew explained, the utility library is actually it's able to change the resolution. So therefore, in the skeleton code, you'll notice that there's a lot of decimal or ratio values. And we have actually gone through and determined these ratio values, so do not change them at all. And these are just so it's scalable, as if you were to change the frame size using that utility library. So then using the given pixel ratios, you're able to determine that sectioned region, as Matthew demonstrated, and as well as we saw in the last OpenCV tutorial. We're then able to actually convert the data type to a float 32-bit and then calculate the product of the given ratio dimensions. And then we're going to warp to, or we're going to create the matrix to warp to, and then we're going to use the warp perspective method to actually get the desired result and then return that frame. So now we're just going to open up the skeleton code for PyCharm. And we should be able to see this first method here, which is under the perspective and region methods. So I'll just give you guys a second to open that. So starting off with getting the perspective, we're first going to determine a frame size. So this frame size is going to be determined by taking our input frame. And then again, as we discussed in the last OpenCV workshop, we're going to be using what's known as indexing. So we're going to index the height and index the width using our dot shape method. So input frame. And we'll start for 1 for width. So this will give us our generalized frame size, which is then going to be able to be scaled depending on these ratios here. So next, we can actually start determining our regions of interest. So we're going to start casting these to a 32-bit. So this will typecast it to a 32-bit float, and then same thing for our end ROI. So now what we're going to do is we're going to start generating our matrices. So our matrices are going to be done by our matrices, our matrix transform. And so this will get a set of vectors to which we want to warp to. So we're just going to name this matrix transformed. And set this to cv2.getPerspective. Transform. And then we're going to start with our initial ROI. And we're going to want to warp to our ending region of interest. So basically what's happening is it's going to take the individual heights that we've started with. So if you think of these points as the vertices of our region of interest, we're then going to change them to the corners of the screen. So these are the defined corner pixel values of each of the 4 corners of the screen. So we're warping our region of interest to each one of the sides of the screen. And so that's what this will do here. And then next, what we can do is we'll then have to warp to those, which we'll do a new warped frame. And we're going to set this to using our CV2 warp perspective. And we're going to take our input frame, our transform matrix, which is matrix transformed, as well as our frame size.
Yeah, Lewis, just slow it down a bit. Just so people can catch up.
Sure. And lastly, we're just going to return the new warped frame. And so now, since we're basically going to be manipulating this one frame and we're warping the perspective and we're going to be doing all of our computations on one given frame, it's important to know that we're not going to want to output that that given frame because it's not going to look like the same as the input video because we've changed it. So we're going to have to actually go back to our original frame. And the way that we can do this is actually by individually changing which perspective we're transforming to. So I've also input a change perspective back method. And this will actually go from one perspective back to the other. And so the only real difference that we need here is just to switch these two values under matrix transformed from the end to the initial. So I'm just going to copy this script here. I'll just do piece by piece. Again, these should be the same, these locations. I wouldn't worry too much about them. And then this. And then our last two pieces here. And so the only real difference between the change perspective back and the change perspective is that we're just going to switch these two values, as I said. So now this one will become end ROI. This one will become initial ROI. And lastly, we're just going to want to return our new warp frame. So I'll just give you guys a minute to copy these two methods down. Just know and just be aware that the change back perspective has the two different spots for the end and initial. So I'll just go up to the change perspective and I'll give you guys a minute to copy that down if you guys missed anything. And if you guys have any questions as well, feel free to ask any of the project devs. We should be available as well. So I'm just going to move on to the next portion, which is going to be within our main method here. So I've pre-scripted part of the main method already, which will include the utility library as well. So I'll just continue. It's around line approximately 210, depends how many spaces you added. In defining our main, first, we're just going to actually start with our while loop, which is going to be inputting our video as our cap.read. And the video input's actually at the very top, so we can't see this here. However, as Matthew explained, we're going to be using what's known as the utility library or the imutils. And this is done from using the frame library and then changing it using resize. So this will allow us to facilitate faster execution of the program by changing this given resolution. And then we can just return our given frame for the rest of the computations to occur. So, and as I said earlier, we also use various indexing for both width and height. So moving on to the main body here, what we're going to do is I'm just going to do a quick demonstration to show you the altered perspective. So, and this is just a variable. And we can actually show this frame right here using the cv2.imShow frame. And I'll just name this alt for altered, and then and so we're able to see how the frame will actually adapt from a regular video. So this is just the general altered perspective that we can see here. And I'll just give you a quick reference as to the difference that we're generating here. So, and we can actually generate a difference by using the CV2 IMShow and then just frame. So we'll denote the original frame as frame and then frame as well here. And we can see the difference. It will fit on my screen. So I'll just explain this one. So we're capturing this region here and then warping it to the individual corners. And this is a lot easier for our program to understand rather than a depth image. So you can see the difference there. And so that's the frame. This altered frame is the one that we're going to be doing most of our computations on. So I'll just get rid of these for now. That was just a quick demonstration to show you what that method does. From here on out, we're going to be doing mainly a lot of separate computations, and we're not going to be able to show them right away. So the thing is that at the end, you'll see kind of, or out throughout the PowerPoint, you'll see various photos on what we're trying to achieve. And so we're going to try and go for that. Unfortunately, I'm not going to be able to show you every single frame as we go because we'd have a ton of IMShow statements, and also the way that I've laid the main method out doesn't facilitate that much functionality. So we will have to go back to the presentation for the next method. So if any of you guys had any issues with this change perspective method, just let one of the project devs know, and then I'll give you a little bit to do that. And then we will be right back. Yep. Okay. So I'm going to move on to the next half now. So the next half will encompass a color filter. So as described in the previous workshop, in the introduction to the OpenCV, this will lead us to our color filtering method. So the color filtering method, which we will be creating, is needed so that we're able to filter out certain colorized features which we would like to know that occur within our warp perspective. And to do this, we're first going to need to convert our color spaces to hue, saturation, and value spaces, or HSV color spaces. And next, we're going to have to declare an index for the values, which we're going to filter out, similar to that of our sticky note example in the last presentation. And then using the upper and lower bounds, we can then determine which colors are going to be filtered out of our image, and then which ones are not. So from this point, we're then going to use the CV2 in range method and determine the values in the given and upper and lower bounds, and then which is in our method. And then we will output a binary image, which looks like the one that you see here on the screen. So as long as the values which are pre-specified in the skeleton code fall between the ranges, they will not be filtered out. So I've set two different ranges for both yellow and white lines. And then now these two lines should be then filtered and then categorized by their own respective filters. And then we can do further computation on those as well. So as I said here, this is what the final image would look like, at least for the white lines on the road. So just a binary image with white and black. So first, to do this, like our previous example, we're going to convert our blue, green, red, or BGR color space to HSV. And then using NumPy arrays, we're going to set the lower and upper bounds for the filter, or our HSV filter, which should be predefined within your skeleton code. Using the CV2 in range method, we're then going to determine if the values are within the lower or upper bounds, and then return this final frame or binary image. So we're then going to go back to our code here. And so first, we're going to start on our yellow, and we need to keep in mind, as I just said, we're going to have both yellow and white. So you cannot just copy and paste these two scripts, because the main issue is that these predefined values will be different for yellow as they are for white. So don't copy and paste them. Just copy and paste little bits and pieces around, because it will be fairly the same. The only major difference is that you're going to have different predefined values for your upper and lower bounds. So I'll just let you guys get there. It's just under the yellow lines comment here. So as I said, we're just going to get started. The HSV space that we need to convert to is the first priority. So we're going to do our conversion. So HSV is equal to, and our cv2.cvt color method, what we're going to be using to convert this color space. We're going to take our given input frame, which is what I've predefined in the skeleton here. And we're then going to use our cv2 built-in methods to then convert that frame. And we're going to convert from BGR to HSV. So next, what we're going to be doing is we're going to use our in-range method using these two values. So this represents the hue, the saturation, and the value for our upper and lower bounds. And using these, we're then going to develop our mask. So our yellow mask is going to be our cv2.inRange method. And this will generate our binary image. And we're then going to put in our new changed HSV space with a yellow lower range and a yellow higher range. And then we're going to finally return our yellow mask. And I will just get you guys to copy that down really quick. So I'll give you a second to catch up if you did fall behind at any point.
Lewis, for some of us, the stream's lagging, so just in case, just go a bit slower because it lags a bit. I'm pretty sure it's just hopping.
Is there a delay?
It just hopping, yeah.
Oh, okay. So now what we're going to be doing is we're going to do the white lines. So next thing, we're going to scroll down just a little bit, and there is a separate white lines color filter. And our next white lines color filter is basically the exact same as our yellow lines color filter. But as I previously described, there is a little bit of difference. So it's just easier for us to copy and paste our HSV. But do be aware that as we do define this, we're going to need to change our mask. So our white mask is going to be equal to our conversion. So we're going to need to make our binary image, so CV2 in range. And now we're going to be using our HSV. And we're going to be taking our lower bound, which is in this case lower white, and upper white. And finally, we will return the white mask. And so again, very little difference, only really spelling is going to be a major concern here. So just make sure that the values, and you can check to see if they're spelled correctly by seeing if they're correlating to the proper array. So I'll just give you guys a minute to catch up on this one. And again, if you guys have any questions, feel free to reach out to some of our project devs. So next, we're going to move on to our CANNY. So now that we've defined a color mask or a binary image, we're then going to be able to do now more computations to this frame. So one of the most important things that we're going to need to do is to edge detect our images. So next, we're going to be determining the edges of our given binary image, which have been processed by the color filtering methods that we just developed. So this can be done by utilizing the CV2 CANNY method. And the CV2 CANNY method will take in the color filtered image or binary image and then determine the edges given identified features within the image. So this will process the edges, which can be later used within computations. So such as CV2 HOUGH lines P. However, some of the input images are they're never perfect. And a perfect example of this is you can see a little dot on the side of what is a yellow line here. So this is not a defined feature that we would like. So to prevent issues, we're then going to have to use Gaussian blurs to blur the image so that our HOUGH lines methods don't set unnecessary vectors as often. And so this is the desired output of the CANNY method, which you can see here, which is for our yellow line. And so to define this, we're going to first start with the CANNY, we're going to input our warped perspective image, and then we're going to use our color filter inside the CANNY method. And then this will return our binary filtered image. And then we're going to use the CV2 CANNY method to determine the edges of the given binary image. And then we're going to iterate a Gaussian blur with a defined kernel size, which we talked about in the first presentation, to perform what's known as image smoothing to reduce unwanted noise. So we'll just go back to the script here. And so this is where we're going to be defining it. We're going to go for the yellow CANNY first. And so for our yellow CANNY method, we're going to start off by creating a count variable. And this is going to be for our loop, which is going to iterate our Gaussian blur. Next, we're going to define a color mask. So we're going to use our previously defined yellow filter, our yellow color filter here, and then we're going to generate our color mask, which we'll define as color mask. And we'll set this equal to yellow color filter, which is right here. Make sure that everything is spelled correctly, and we're going to put in our input frame. Next, we're going to use our CANNY CV2 CANNY method to make a CANNY detected image or an edge detected image. And this is done using our CV2 CANNY method. So we're going to name this variable our CANNY image. And we're just going to set this equal to cv2.canny, which will take in our image, which is our binary image, which is our color mask, as well as some additional parameters for our thresholding. So for this program specifically, these can change based on the program that you have. We're going to be using for our first threshold 50 and our upper threshold of 150. And these just work best for at least the video input that we have here. Next, we're going to be determining our while loop for our iteration of our Gaussian blur. So we're going to do while count is 5. We're going to do count plus equals, which just adds 1 to our given count every time it's looped. And then we're going to use CANNY is equal to CV2 dot Gaussian blur. And now this is going to blur our image. So we're removing our noises from the given image. It is extremely important for our next following steps. And we're going to use our CANNY image for this. And we're going to define a kernel size or a K size. Now, as Matthew explained in the last presentation, you're able to think of our kernel as a similar paintbrush, which every time it passes over, it's going to merge some pixels or change pixels to different values to lose details within our given binary image. And so we're going to define a kernel size of 5 by 5. And now our last value of sigma x is just going to be 0. And just set this to 0. It's a little bit detailed, and I'm not going to get into why it's set to 0. So this is going to be our CANNY method for at least our lane detection program. So I'll just give you guys a minute here to copy this down. Again, if you guys have any questions or concerns, feel free to reach out to the project devs. So now we're going to move on to developing our white CANNY. So again, we have both yellow and white. So the next important thing is to, we're going to be doing a very similar thing to this for our white lines. In fact, it's basically the same. So if we'll go down to our white CANNY, white CANNY is going to be, again, we're going to iterate our count. We're going to need to start a value or initialize a count at 0. We're then going to determine a color mask. And this time we're going to define it as a white color mask. So we're going to use our white color filter method that we made. And we're going to use our input frame. From this point, we're then going to determine our CANNY image. So our CANNY image is going to be CANNY underscore image, as we did in our yellow lines. And we're going to be doing cv2.canny, which is our inbuilt CANNY method into our OpenCV library. This will use our color mask, which we just defined, as well as our threshold values of 50 and 150 for our CANNY method. Next, we're going to move on to, again, iterating our Gaussian blur. And this is done again with our while loop. Inserting count less than 5. And our count, which is plus equals 1. And our CANNY is going to be our CANNY image. It's going to be equal to cv2 dot Gaussian blur. And this is going to be blurring our image. We're going to input our CANNY image. And we're going to have a kernel size of 5 and 5, as I previously described on the last method. It's basically the exact same. And we're going to want 0. And now this time, we're going to want to return CANNY. And so now I'll give you just a minute to copy that down or to catch up. So now we're going to start filling in our main method. However, I'm just going to go over some next quick things in our PowerPoint. So next, what we're going to be doing is we're going to be going over OpenCV HOUGH lines. So as I previously described in the introductory of how this works, our main method, or sorry, our HOUGH lines is crucial for the function of operations of lane detection. And this is done using a set of vectors and the vectors that it returns. So when using a CANNY edge detected image, such as the one that we used on the previous slide, we can then use this to place into our HOUGH lines probabilistic methods. And this will return a crucial set of vectors where in OpenCV, we're able to make user-defined geometries on our screen, as you can kind of see with these, this card here, how it's detected the edges, first using CANNY, and then it will return points as to where it saw the lines or where it's estimated the lines to be. So then as programmers, we're able to fit a line to this given space or this given vector. So we can utilize these vectors in different ways to allow us to achieve certain computations for our given input image. And using the HOUGH lines probabilistic method requires some additional parameters, or additional arguments, which are listed right there. I'm just going to have Matthew copy and paste them directly into the chat. So from there, we can then move on to the next piece of our code. And so our CV2 HOUGH lines method is going to be developed within our main method. So if you could scroll down to main right now, and we'll get started. And it's going to be just defined after we specify our CANNY images. So as I explained in the slides, it's very important for us to have a CANNY image. So to use our HOUGH lines, which is our edge detected, our CANNY images are our edge detected images. So we're going to define our yellow CANNY images. And this is done using our yellow CANNY method. And to do this, we're going to put in our altered perspective as our input frame. And what we're going to be doing is we're then going to be using our white lines, or our white CANNY. We need to determine our CANNY image. So we're going to do white underscore CANNY image. And then set this equal to white CANNY, or white CANNY. And use our altered perspective. So now that we have two different images, or two different edge detected images, we're then able to actually develop our HOUGH lines, or our vectors, or a set of vectors. So underneath, we're going to develop two sets of vectors, one for yellow lines and one for white lines. So I'm going to do yellow lines equals CV2 dot HOUGH lines. And important to use, make sure that you're not using HOUGH lines, but you're using HOUGH lines P. This is very important. If you use HOUGH lines, it will not work. So just keep that in mind. So what we're going to do now is we're going to input our yellow lines, or our yellow CANNY image. And we're going to paste the values that should be in the chat. Just let me make sure that they're there. Yep, so Matthew has put them in the chat there. So just use those values. And now what we're going to do, just to save a little bit of time, we're going to copy this. And we're just going to paste this. And now make sure to change this to white lines. So I'll try to encompass most of this on my screen so you guys can see it. And I'll give you just a minute there to catch up if any of you guys did fall behind.
and Nurjan, if you want to do the talk about the survey, now's a good time. In the chat, there's just a link for our survey. It's basically just to give us feedback and try and make the workshops better if you think they're not good, or just tell if we're doing a good job. And just basically a basic survey about how you like the workshop and what happened in it.
Yeah, so let us know what you think, and that'd be awesome.
Yeah.
So we'll just take a quick 5-minute break here, so for an opportunity for anybody who would like to fill out the survey. And yeah, we will be back in 5 minutes.
Hey guys, yeah, just like Matthew and Lewis said, if you guys could fill out the feedback form in the next few minutes before we continue with the rest of the workshop, we'd really appreciate your feedback, just because we're just starting to do these online-based workshops. So any of your input would really help us do better next time. So yeah, before Matthew and Lewis start, if you could just click the link, it should take you about a minute. Of your time, or you can do it after the workshop as well. But if, we really appreciate if you can give us your input.
So this should have been hopefully enough time to fill out a survey, and yeah, we're gonna move on to the next portion of our code, which is our draw lines. So now that we've defined a set of specific vectors, and we actually have locations on our image as to where that we would want to place any given lines or geometry, we're now going to specify where we want the geometry to be drawn. And this is going to be done in our draw lines method. So just going back to our slides here, this will bring us to the draw lines method, which will draw lines on the given road and over or outlining desired features. Since that we've acquired a set of vectors through the HOUGH lines method, we're able to then determine where the lines need to be placed. And as seen on this slide, we're actually able to see the yellow lines in purple and the white lines in red. So first we have to make a copy of the given input frame and then make an exact copy using the NP copy method. And the same is done again, however, this time we're going to be doing it with a zeros layer. And so this is important because we don't want to write any lines directly to the input frame. And the reason that we don't want to write any lines directly to the input frame is it can cause issues with gamma, like gamma adding or gamma multiplication. So we want to add them to a zeros layer and then add them merged after. So this is the lines that we've defined on our zeros layer. And the purpose of a copy or NP copy or NP zeros underscore like methods is to generate an exact size frame that we have of our input array in both zeros layer, which is our black image that you can see here without the lines, as well as a copy image to then add to that. So we will then have to determine if there are any HOUGH line vectors that are actually being read by HOUGH lines. So it's important that we're going to be using and checking if there are actually any Booleans. So if it's bool true or bool false. And this is because if it is false and we're checking to draw lines, our program will, or if we are not checking to draw lines, our program will actually crash because it's expecting vectors and we're not giving it any vectors. So it's important that we include an NP any method, which just returns true or false to see if there's quote unquote any vectors or any lines, basically. And then from this point, we can then loop through each one of the given line vectors to store the desired data under the variables that we're going to define later in the code, and then utilize this stored information to generate a polyline along the given line vector. And so these are the polylines here. And I've just colored them differently so you're able to tell the difference between yellow and white lines. And so white is red and yellow is purple. We're then gonna like merge the frames together at the end. So now you have to think of it as we have 3 different frames, and these 3 different frames all need to be added before we return a final image from our draw lines method. And so this is done using the merge methods, which we talked about in the first OpenCV presentation. So the 2 add methods that we're going to be using are CV2 add weighted and CV2 add. And so it's important to know that the CV2 add weighted has a gamma value that we're able to manipulate. So we're actually reducing the amount of I guess you could call it noise in the background to exactly what's being added on top of all the other images. Because when you add many, many images on top of each other, it almost creates, in the given region, it almost creates like a white overlay or a white filter. And we want to remove that using our gamma, or modifying our gamma value. And so it's important to know if there are no lines detected that that we return all of our merged frames without any predefined geometry on them. So next, basic overview of our draw lines method is we're first going to draw the lines on the frame to detect the lane lines. And so that's the purpose of it. And so first we're going to define a copy, as I just said, which is to be drawn on and then merged to the final frames. We're then going to use an if condition to determine if any of the lines have been detected on the screen. And as I said earlier, the HOUGH lines will actually return a set of vectors. So we can actually loop through these vectors to get our x1, our y1, and our x2 and y2 vectors, which are the start of the line, which would represent x1, y1, and the end of the line, which is x2, y2. And then we can store these given vectors in an array, and then we can use them for later computations. So lastly, we're then going to merge the copy frames in the initial frames. And then finally, we're going to merge all the frames together using our weighted frames. So I'm just going to go back to the code here. And now we're going to scroll up to one of our methods here, which should be, there's going to be two different ones. There's going to be one for yellow and white as well. Draw lines, here it is. So it's just under the yellow CANNY method. And this is just for yellow. So I'll let you guys find that. And so hopefully you've found it by now. And what we're going to do, as I said, we're going to start a copy frame, and then we're also going to do a single line frame. So we're going to do our copy frame. And we're going to be doing our MP copy of our input frame. Now we're going to be doing our line frame, and these are just black frames. So, and this is achieved through NP zeros. So this just makes a, and then underscore like. This makes an exact same size array with just a set of zeros in it, which is very useful for us, as you'll see.
This is zeros, not zero.
Oh yes, true. Zeros. So now, next we're gonna do is we're gonna use our mp.any, and we're actually gonna check to make sure that there are any vectors that are in the are being inputted into our method. So mp.any, and we're gonna check for yellow lines. And then we're gonna start looping through all of our vectors for our first condition to see if there are lines. So if there are lines, we're gonna want to do for any yellow lines, yellow line, there's yellow line in yellow lines. And yellow lines like that. And then we're going to do our second nested loop, which is going to be for all of our x1 values, our y2 values, or sorry, y1, x2, and y2 in yellow line. And from here, we're going to determine the exact locations, and we're just going to define this as locations. So we're going to break it up as starting and ending within our MP array. So we're going to do locations is equal to np.array. And we're just going to make this a tuple. So make sure not to forget the square brackets here inside the array. And then we're going to start with x1, y1. And so that's our start. And then we're going to define our end as a separate array. That's x2 and y2. And now that we have the given locations, such as our start and end points, we're actually able to define a given polyline using the geometry methods, which are actually on your CV2 or your OpenCV method sheet, which is cv2.polylines. And this will take in our line frame, which is our zeros layer, our given locations. And it's important that we're putting this in as an array. So make sure to put square brackets around locations here, as well as we're going to define if the line is closed or not. In this case, the line is not closed. So we're going to put false. We're going to be defining a color. Oops. We're going to define a color for our line, and I said for our yellow lines, we're going to do purple, which is going to be 255, which is the max value, 0, and 255. If you want, you can change these colors to whatever you'd like. It will just effectively change the yellow line's color, and it will be inherently different than what I've shown you. But I mean, the output should be similar. It'll just be a different color. And then we're going to define a thickness of 3, which is just a general thickness. Next, what we're going to be doing is we're going to define our copy frames. So we're going to start merging all of our frames together outside of our first for loop. So our first thing that we're going to do is we're going to add our weighted frames or our copy frames together, which are going to be our input and our copy. So to do this, we're going to do our copy frame. And we're going to add our cv2.addWeighted using our addWeighted method. And this is a built-in method to OpenCV. And then we're going to be doing our input frame as well as our given weight, which in this case, we want to add them equally together. Oops. We want to add them equally together. So we're going to use 50% on either side. And then the same thing goes with our given copy frame. So we're going to add input and copy together. Input, copy, and then again, 50%. So each one of them has 50%. And like I said, we're going to modify the gamma value to negative 400. And lastly, for this given input condition or this given if condition, we're going to do our final merge frame. And we're going to do cv2.add, which is another built-in method. And we're going to merge our copy frame with our line frame. And so this will add the lines to our final frame. From this point, we can then return our final merge frame. So I'll just let you guys get this down for a second, and I'll give you guys a minute.
So I just removed the second return statement.
Oh, I'm gonna use it later for our else.
Okay, got you. Oh yeah, got you.
Because we have you need the corresponding else.
Yeah. Oh yeah, this. look at the
Yes.
color imply lines. The argument.
Oh, There we go.
Also, does it matter if it's Canadian spelling or American spelling, or does it not mind?
Oh, yes, you actually have a point. Color. Yes, they were Americans made OpenCV, so make sure that you spell color the American way. That might be that's a possible error. So what I'm going to do is I'm going to move on to the next else statement, which is fairly simple. So this is just the fail statement for if we haven't detected any lines. So if we don't detect any lines, all we're going to be doing is we're going to be making a copy frame, as well as we're going to be doing our mp.copy frame, mp copy, and our input frame. So this is then going to be added to our merge frame. And do CV2 add weighted. And this is going to be using the input frame. Again, we're just going to be using basically the exact same line up here, so you can copy the arguments. And don't forget, finally, make sure this is tabbed correctly, as well as adding your final return for your else, which would be merge frame. So now what we're going to be doing is we're going to be moving on to our white lines. So now that we've found the inDrawn for our yellow lines, we're going to define for our white lines. So there's a separate drawLines method as well down here for this. And more or less, all we're going to be doing is copying and pasting everything that we have up here, except for a couple changes that we will make. So just grab all this. And we're going to go down to our white draw lines. And do this, like this. And now we need to make sure that we're going to be taking the proper frame. So just take this white lines here, copy it, and then we're going to go through and we're going to redefine all of our vectors. And I'll give you guys a second to get that all done. So moving on to one of our final methods, we have a couple more to do. The next few methods that we're going to be working on are going to be our add result methods. So our add result methods are the fundamentals for the operation of the center arrow line, and these are the determination of the direction which the arrow line points. These functions will generate and operate on the basis of the vectors which are computed from the CV2 HOUGH P method previously defined in the last section, and thus they are passed through each of the nested methods. And you can see here we have yellow and white lines. So we're just returning a vector basically. Within the add result method, we are able to determine the approximate center of the lanes utilizing the returned second x values from both yellow and white lines. By doing this, we can then determine the approximate center, which is determined with the center line method. And I've included the center line method in the skeleton code just because it's a little bit finicky logic-wise, and there was a high chance of error with that one. So as we tested multiple times, so I think yeah, I'm going to be going through and explaining it and how it works, but we will not be typing that one out. So the purpose of the add result method is that it takes in the values of the yellow and white lines and it stores the second x value in for later processing as a return. So from here, we're then going to loop through within each one of the yellow lines and white lines. We're going to loop through again in our x1 and x2 values, and then store the given vectors in an array and return the values. So from here, we can then go back to our program, and we're going to go down to our, this is just the center car method. We'll talk about it next, but we're going to go down to our basic arithmetic methods right here. So we're going to start off with our yellow lines. So, sorry, yes, yellow lines. And we're going to determine our if statement. So like I said earlier on our HOUGH lines, or sorry, our draw lines, we need to determine if there are any lines. So to do that, np any, and this will return the Boolean condition that we need. So our program doesn't crash if there's no lines. And we're going to input yellow lines, which is our vectors. So for any of the yellow lines, or yellow line, so I'll just do yellow lines and then get rid of the S, important, in yellow lines, we're going to loop through each one of the x1, again, y1, x2, y2 values in yellow line. And we're going to want to return the x2 value. So the x2 value is extremely important. I didn't want to use the x1 value because it could be too, or possibly too far away, and I don't want the arrow to cross over any of the lines. I want it to stay relatively centered, so I decided to use the x2 value in this case. So to do this, we're going to be using our NP arrays, as I said on the slide, and we're then going to store our x2 value within this as its own array. And finally, we're going to return our x2 value. Lastly, we need to make sure that we have a corresponding else statement for this. And our corresponding else statement is going to just state that we're returning 0 as our array. Or nothing really stored in the array. Just be an array of 0. And the same thing is going to go for our white lines. So it's basically the exact same. So we can copy this here and we can move down to our white lines. The only difference, again, is we're going to make sure that our arguments correspond to the correct locations. So we're going to have to change all of these to white lines. So I'll just go down to here. Lines. And so these will give us our x value for our second x value for both white and yellow lines. Oh, and make sure that the return statement is moved over to correspond with this outside of the loop. Make sure it's outside of the loops on both yellow and white lines. So I'll just give you a minute there to copy that down if you guys fell behind on anything. So moving on to the next method within this group of basic arithmetic functions, our user-defined functions, we're going to start by taking our methods that we just defined, or our user-defined functions here, and we're going to start defining other arithmetics with them. So we're going to do yellow underscore lines. Line. So these will give us, and we're just going to categorize the points here. So we know that they're returning the second x value. So we're going to categorize our yellow and our white lines, get them into variables. For a given set of vectors, yellow lines. And then the same thing will go with white lines. And now we're just going to find the halfway point between these two x values, given that they're on the same y point. So now I'll just give a demonstration with paint. So what we've effectively done is we've taken two road lines like this, and we've found, given the same y value here, constant y value, so if we graph this, all the points, since we've only returned an x, the only thing that will vary is our x point, which is in the x direction. So now from here, we're able to find, based on the point or the second x point here and here, if there's a line there, we can find the center between the two lines, which is what we would like to find for our add result method or our arithmetic. And so this is going to be the basis of where the center of the arrow will point. And so we want this location right here. So to do this, what we're going to do is we're then going to take our result. So we have our 2 points here and here, and we're going to take our result and then equal it to white lines, or white lines point, and we're going to add the two, and we're just going to find a mean. And we're just going to divide this by 2. And so from here, we're going to return the result. So this will be the arithmetic which will be used in our final center line method. So in our final center line method, I'm just going to go back. One second. I'm hoping you guys could have copied this down as I was explaining it. If you guys need any help, just reach out to any of the project devs. We're just running a little bit short on time here, so I'm going to move on to the centerline method for time's sake. So moving on to the center car method, this will take a little bit to explain. So this will lead us into the final method that we're going to be using or defining within our center or within our car and lane detection program. And so due to the complexity, as I explained, we've included it. And so the center lane method utilizes the arguments of the input frame and the given line vectors and frame width and height values. So first, what's done is a copy of the input frames is made using the NP copy, and the same thing goes with the line frame as we've seen in previous methods. So first, we'll specify the origin of our given line and ensure that it's in the center of our car. And this is going to remain static for where our origin of the arrow is here. So this represents this small point here. So, and this is the approximate center of the car. And so from here, based on these values, which I've turned also into ratios, because again, we can scale this using the IM utility library. We're then going to be able to find a final point, which is where the average or the average distance between the two lanes will be. And then that's the direction that the car should be traveling approximately for our basic path prediction to stay between the two lines. So this will take the values from our add results for the center point and then assign them to the result and result I variables. And the result I is just the initial result, which is specified in main. It's just an initial variable of 0. And then that will change depending on how these averages come out. So I'm just going to go right into the script here, and I'll explain it line by line. So the first major breakdown and the thing that is very important for us is that for these given lines here, we're going to check that there are any vectors, again, for both yellow and white lines. And I've assigned a direction sensitivity because the major issue with center lines is that it's going to stutter between because it's reading all the values so quickly. So we need to be able to basically make a threshold, meaning the tip of the line should only change if it surpassed a certain number of pixels in either direction. And so what I've done is in these given if statements, I've defined regions of interest on either side of the screen. So if we go over back to our paint here, if I draw my screen like this, I've defined both a left side, a center, and a right side. So because we know that the dot is going to be placed somewhere here or anywhere along this axis, or the same constant y value, we're then able to say, well, given these bounds here, if the dot passes into this region, the car should be turning in a specific direction, or if the dot passes into this direction, it should be turning in this direction. And so we can then predict where the car should be turning. And so again, if it's within the center here, it will be turning, or well, it won't be turning, it will be going straight. And so I've actually left some open-endedness to this method here. So if you guys want to adapt this code, feel free to add a little bit more functionality if you'd like, maybe adding a center to turn left and or right, or going center. And it's very open-ended. So it's a fun little project if you decide to work on it outside of this. And so this is done again. So we're determining our initial results, and these results are returned from our add result method, which is our arithmetic. And then we're just comparing it to our array to determine if it is within one of these given regions. And if it's in one of these given regions here, we can determine that the car is turning left, right, or going center. And so we're just going to draw the arrow pointing in these directions on each one of them. You can also add text here as well. And then we're going to return, again, we're going to merge all of our frames as we've seen in previous methods, and then return these results. And then the same thing goes for the other ones, just with different logical conditions. And yeah. So this is our copy or center car method here. And so lastly, what we're going to be moving on is our main method. So we're going to start moving on to the final program and just building the rest of it just in our main here. So if we go down to main, from here, we're going to then finish it up. And we're going to do this by using or starting off with our yellow lines frames. So we're going to start drawing on our perspectives. So I'm going to do yellow lines underscore frame. And we're going to draw lines on our given perspective. So we're going to do this, we're going to put in our altered perspective, which was the first method that we defined. And we're going to now use our brand new yellow lines method. From this point, we can then define our white lines. White lines frame. And we're going to do our white lines or white draw lines, which is here. And we're going to take in our altered perspective again, and we're going to be drawing our white lines. So from this point, now that we've drawn all of our lines, we need to add our center line. And so this can be done by defining a center line. And as you saw in our center line method, we're actually returning 2 results. And so we're going to need these 2 results and we're going to index them accordingly. So just going down to our main method again, we're going to determine a center lane. As well as a result, an initial result. And we're going to set this equal to our center car method. And so I've set up the center car method to take in several different parameters, such as our altered perspective, our yellow lines, our white lines, our result, initial, which is our predefined value here. It's just 0 initially. And our width and height. So lastly, we're going to start adding all of our frames together to generate a final image. And this is going to be done through line frame equals cv2 dot add. And we're going to be adding our yellow lines frames together and our white lines frames. And so this will get them all on the same frame. And now we just need to add our center line to these final frames. So new lines frame. And then cv2 dot add. And we're going to do our line frame to our center line, center lane. Now we have to, since we're all in the warp perspective, and I said that we were computing everything on our warp perspective, we need to back perspective it. So we're going to be doing this with our back perspective method, or our change perspective back method. And we define this at the beginning. And this is going to take in our new lines frame, which is everything that we've added, all of our geometry, which we now want to put back. And lastly, we're then going to go to our processed frame. And we'll put our back perspective here and our frame. So this will add our final, and then this is our final processed frame. So everything should be good from this point out. And now we can display our final image using IMShow. Our wait keys are there. And so as we can see, oh, I forgot to change the color of the white lines here.
Mhm.
But as we, oh,
Okay.
pardon?
No, yeah, no, yeah, the color I was gonna say.
Yeah, so you can see that the lines are purple here. And so to change the actual color, we can then go through and we can go back to our draw lines, which was right up here for our white draw lines. And since we just copy and pasted it, that was my mistake. We can actually just change it to red. So this should be 0. So BGR. And if we rerun this, now our lines are red. So you can see how we can adapt this. And this is our general center line as well. You can see how this runs. So I'll just quickly go back down to the final method here. I don't know how well you guys can see it. I know that there was a little hiccup with regards to the being able to see the text because it was so small in the first presentation. So if you guys need any adjustments or you guys have any error, again, feel free to reach out to our project devs. So this is the new section here that we just added. Feel free to reach out to any of our project devs and we can try and fix the error. I think we're also going to be pasting a text file as well to all the completed code. So if you'd like to look over it or we can't fix any of the errors that you may possibly have in your given program, then yeah, we can take that action as well and you guys will at least have the completed code. So this is the final result of our hard work over the last 2 hours. And as you can see, we're now able to path predict for a vehicle between 2 different lanes. So I'm just going to finish up the presentation here. So just our main method breakdown finally, are resizing the image as Matthew talked about initially, getting the vertices, determining our region using our warp perspectives, calling the user functions, determining edge detected images, using the edge detected images for our HOUGH line methods, and drawing the lines and then combining the frames together to finally develop our result here. And so thank you all for attending our 2-part workshop. And that is the conclusion. I'll just leave the code up here for anybody that is trying to copy down the remaining bits and pieces. And I'm not sure if Nurujin has or Abhishek has a final statement to make. But yeah, thank you.
Yeah, if you have any issues, just please let us know.
Thank you so much, Matthew and Lewis. No, you guys said everything that we needed to say. We just wanted to thank you guys for coming out to both a 2-parter. This was our first time ever doing a 2-part series for a workshop. So just like I reiterated before, if you guys can give us your opinions and thoughts about how these past 2 workshops went, or specifically this one, we would love to know whether that's the way we teach it, the way we broadcast it, the content, is it relevant? So any of that would be greatly appreciated. But I, at the same time, thank you again for coming to our workshop. Hopefully you're able to take something away or get something started based on what Matthew and Lewis taught you today. And also, like they said, we will be sending the final code after this workshop. So keep posted on that. If not, you guys are free to leave. I know Lewis has his presentation up, so if you're still working on, that's fine. But if you're good, you're good to go. Thank you, guys.